So, welcome back. Today we're going to start getting serious, learn how to scale up reinforcement learning to real practical problems. By the end of today's class, hopefully you'll be able to go off into the world and actually program interesting reinforcement learning agents that can solve problems. In fact, we'll see state-of-the-art results, and you'll really get to the point where you're there, where you can see the whole algorithms do policy evaluation, do control, using function approximators to represent the value function. That's the key idea for today. The outline is going to be fairly simple today. We'll start off just understanding the basic space we're working in, and then we're going to split things up into two different approaches. First of all, we're going to start with incremental methods. Really, this approach is to say you take some function approximator like a neural network, and incrementally, every single step you see some new piece of data, it comes in, and immediately online you take some step to update your value function online. And then we'll start looking at more data efficient methods that kind of look at the whole history of everything you've seen so far, and start to look at the whole set of data and start to exactly fit your value function to everything you've seen so far. So roughly we're calling those batch methods. You can think of this also as online methods. The split is a little bit grey, as we'll see, and there's certain methods which work very well here that build on some of the ideas that we use here. So it's not quite as clear-cut, but I think it's a helpful distinction to understand the space of value function approximation methods. So why are we interested in value function approximation? What's wrong with the story so far? Well, we'd like to use reinforcement learning to solve large, real-world, interesting problems. So how large do problems get? Let's just get a sense of scale, first of all. So if we think about some of the problems that people have solved, I've worked a lot in games, and in games you often see numbers like this, where the game of backgammon is considered a very small game for working in games. That's got just 10 to the 20 states. If you work in something like Go, there's 10 to the 170 states. But if you work with robots in continuous state space, there's an uncountably infinite number of states in this domain. So something's got to give. You can't just build a table anymore. The approach we've seen so far of just building a table and having a separate value for each state in your state space is just not practical. It's not going to work. It's not going to scale up to these interesting problems. So we need some method that scales up, and regardless of the size of the state space, we want to be able to get methods that work. We'd like methods that work with infinitely large state spaces, and you just happen to build a function approximator that estimates the value of just the parts of the space which you visit and know about, and which generalizes across parts of those space so that you don't separately represent the value of being here from the value of 1 millimeter over to the right. Intuitively, the value of those states should be pretty similar, and we want our value functions to understand that generalization without having to separately store a distinct value for each of these states. So that's the goal of today's lecture, is to understand how to achieve that generalization and to build up efficient methods for both representing and learning value functions in reinforcement learning. In the next class, we'll look at other approaches to using function approximation for policy space algorithms rather than value-based. We'll look at policy-based algorithms. But today, we're really going to focus on value functions. How can we scale up? Value functions have been the central idea we've seen so far. And so in particular, we want to know how to do the core ideas that we've seen so far, both prediction, how to evaluate a policy, and also how to do control. These are the main subjects of the last two lectures, and we want to scale them both up. We want to be able to achieve good results with both of these ideas, both of these paradigms. So here's the basic idea in a nutshell. So far, we've really looked at this value function. We've had some value function v of s, and this v has represented some kind of lookup table. So for every state, or for every state action pair, there's been a single value stored. So for v, there's been like a single value per state, and we built this big table that said, for every distinct s, there's going to be a value v of s, and we were then able to build algorithms that manipulated those v of s's to figure out the problem and pick the right actions and solve the MDP. When we wanted to do control, if you remember, with control, we need to be able to pick our actions without using a model if we want to do model-free control. So we needed to use an action value function, q, that lets us consider for each state and for each action separately, what's the value of taking that action A in that state S. And this q, this action value function was sufficient to do control, because if we have this thing, we can immediately pick our actions by maximizing over our A's in each state, S. But again, so far we were just restricting ourselves to this giant table that has for every state and also for every action now. So think of this as like a two-dimensional table for all states in your state space and all actions in your action space. We had a separate entry in the table. Okay. And so let's be specific about the problem now. There are just too many states and or actions to store in memory. That's the first problem. But also, even if you can store it in memory, if you've got such a vast state space, like let's say you fill up your whole memory, you've got, a few gigabytes of memory, maybe you can build just a really, really large table and represent your MDP. But even if you do that, it's going to be too slow to learn about them all. In practice, we don't want to see trajectories that estimate the value of each of those states and actions separately. It's just going to be too slow. You need too much data. And so what's the solution? The solution is value function approximation. And we can basically represent the idea very simply in this following way. So what we're going to do is we're going to consider the true value function, v pi of s, as just some function mapping from s to the true value of v of pi. And what we're going to do is try and build some function that estimates this thing everywhere. So if you feed it in any s, it will give you some estimate of this v pi of s. And the way we do that, we're going to consider parametric function approximators that have some parameter vector w. So w is just some vector of weights. Think of this as the parameters of your neural network, or if you have a linear combination of features, it's going to be the weights of those features. And we're going to estimate our value function by building some function approximator that fits this thing across the whole state space. So we're going to try and fit this using some compact representation that's going to have a smaller number of weights, typically, than the number of states in the state space. So using a small number of parameters, we can now fit this thing everywhere, and we don't have to have a single entry for each state in the state space. And alternatively, we can do the same idea for the action value function, where we can try and fit the true action value function, q pi, which tells you how good is it to take action A from state S. And we're going to just consider that as this big function. That for any S and any A, we should be able to query this function. And we want to fit that function for all S's and all A's. We want to just fit this thing so that now if we feed in our S and our A, which is going to have some vector of weights, again, this could be the weights in your neural network, we're going to try and fit some function approximator that estimates this thing everywhere across the whole state space and the whole action space. I'm just going to think of that as a big function and try and fit that function. And what this is going to enable us to do is not just reduce the memory, so we can reduce the memory if there's a smaller number of weights than we had states. It's not just going to reduce the memory, it's also going to allow us to generalize. And the reason it allows us to generalize is because we can fit our function to states that we've seen, and we can generalize to states that we haven't seen by querying our function approximator at points that we've never actually seen so far. And the way we're going to do this then, so we'll get into more detail so we don't have to understand everything from this slide, but the way we're going to do this is basically, we're going to think of this parameter vector, the weights of our neural network. We're going to update these things using the methods that we've seen in the last couple of lectures, Monte Carlo learning, TD lambda, and so forth. That's going to give us the targets for adjusting, for fitting our function approximator so that we can start to understand how to get the right value function. But before we do that, what we're going to do is, before we understand how to do the Monte Carlo or TD learning, we're just going to focus on what it means to do function approximation with a value function. So this slide basically shows us 3 different types of function approximation we can use with value functions. So these are like different architectures you could use. I tend to think of a neural network as a canonical black box function approximator, but you can use anything you like as this black box, any function approximator at all. They're all valid for reinforcement learning. Okay? And the idea is, if we're just trying to do state value function approximation, you've got this black box here, you feed in your state here, you've got something like a neural network that's going to kind of represent, this wiggly line is supposed to represent the fact that there's some internal function that this thing is trying to fit and represent, using some internal parameter vector w. And the way in which w affects this is just part of this black box. We don't worry about that. And what this thing is going to spit out is the value function at this query state S. So we feed in S. This thing estimates how good is it to be in S. So we feed in, I'm in this state over here, and this thing says, aha, you're going to get 7.6 units of reward discounted over the rest of your trajectory. Now, when we do action value function approximation, we've got 2 choices. We sometimes call this action in and action out action value function approximation. So in the action in case, what we're going to do is say, okay, I'm in this state here, and I'm considering this action here. How good would that be? And there's this black box here which is fitting some function across all states and all actions using some parameter vector w, and it spits out its estimate of how good it is to take that particular action in that particular state. Sometimes it's more efficient to use a different form. It's equivalent in its, the actual data that it's representing is the same, but it leads to a different training algorithm and sometimes a more efficient or less efficient result depending on the context. And now we're just going to say, hey, a state comes in, and we want our function approximator to tell us the value of all actions that I might take. So just the advantage of this is in a single forward pass, this thing could spit out the values of all the different actions. So we use this in Atari, for example. In one forward pass, we can say how good is it to move the joystick left, to move the joystick right, up, down, press the fire button. And just in one forward pass of your neural network, you get all of the information required to be able to make a decision. You don't have to feed it back in with different actions again and again and again. So these are all mechanisms for value function approximation. And the basic idea you should be trying to get your head around is that there's some representation of how good it is to be in a particular state, and we're trying to generalize across the whole state space using this sort of tunable parameter vector. So we're going to try and fit something to the true value function. So we want the shape of this internal kind of curve, this surface we're building, to be as close as possible to the true value function, so that now for any state that we query, we get the right answer. I'm going to train these things up to give us the right answer. And the way we do that is how the reinforcement learning comes in. Is that clear so far? Good. So let's open up the black box a little bit now, and ask the question, well, what should it be? What type of function approximator? So hopefully, during your experience of the machine learning masters or whatever else you're doing, you've come across a whole variety of different function approximators for supervised learning or perhaps unsupervised learning. Some of the most common ones are listed here: linear combinations of features, neural networks, decision trees, nearest neighbor, Fourier or wavelet bases. There's a whole bunch of different things you might try. And you might ask, well, how can I navigate this sea of possible different function approximators? So for reinforcement learning, well, at least for this class, what we're going to do is focus on differentiable function approximators. So these are function approximators where it's relatively straightforward to adjust the parameter vector because we know the gradient of our function approximator. We know how, if we change these w's, these things tell us if we change the w's, how will that affect the v that comes out. So we know that gradient. If we know that gradient, there's a set of tools that we can bring to bear which allow us to do a certain class of algorithms that can be quite efficient, incremental, have nice properties. So for example, we're going to focus today on linear combinations of features as the canonical case. We'll see a little bit more what that means, but also allow for nonlinear function approximators like neural networks. And these are examples of differentiable function approximators where we know exactly how, if you change the w in your neural net, we know exactly how that affects the outcome, because you do a backward pass on your neural network, that gives you your gradient. Similarly with these linear combinations, we know exactly how the gradient of these things. So that's the representation. We want a representation that's differentiable, but what about training these things? Well, what's special about reinforcement learning compared to supervised learning is that in practice we end up with this non-stationary sequence of value functions that we're trying to estimate. If we're trying to estimate v of pi with this thing, we want this thing to evaluate our current policy, but our policy is changing. Our policy is going to improve. Like when we start to do control, we're going to start off with, say, some random policy. We want to evaluate that random policy, fit a value function to it, and then we're going to improve our policy, and we want to fit that new, better policy, and then we're going to change the shape of this is going to sort of slightly adjust as we get better and better at navigating our domain. Sometimes it dramatically changes. You figure out how to get into a new room that you've never seen before. The shape of your value function suddenly changes because you discovered a big treasure in that room or a pit of snakes or whatever it is. So we need to allow for non-stationarity in our in our function approximator, in the way we train them. And we need to allow for non-IID data. This is not supervised learning. The data that, as it arrives in trajectories that we're following, and where I am now is very highly correlated with where I am at the next step. And so IID training methods are typically not effective, or at least we need to be smart about how we make use of them. So that's the challenge. We're going to try and make use of these tools, put them together in a way that lets us do RL at scale. And the methods are relatively straightforward. Okay, so we're going to start by looking at incremental ways to do this using stochastic gradient descent to achieve incremental value function approximation. And then we're going to move on to batch methods such as least squares methods. Okay, so let's start off with gradient descent. So first of all, show of hands. So who is familiar with stochastic gradient descent? Good. Okay, I think that was almost everyone. I'll go through it briefly. I think it's good just to make the notation clear, make sure even if you're familiar that we're going to make heavy use of this over the next few slides. So we're going to consider some function. This is just gradient descent in general before we move to our value function approximation. So let's just consider some differentiable function j with parameter vector w. And we're going to use this definition of gradient, this sort of grad w notation. And what we're going to find the gradient vector to be is the gradient of partial derivatives with respect to each of our parameters in turn. So this vector basically tells us the direction of steepest descent, or steepest ascent. And we're going to follow this downhill. So this thing tells us, if I'm on some surface, which way is it to go down? And I want to follow that down my surface in the steepest possible way. And our algorithm is simply to say, to find a local minimum of this, we're just going to adjust our parameters in the downhill direction. So we're going to adjust our parameters to move down and down and down until we minimize this, this function, which we haven't defined, but this is our objective function. Or some objective that gives us a surface. We want to move down to find a minimum of that objective function. And all we're going to do is adjust our parameters a little bit downwards. That's the minus here. The half is just to make everything neat in the maths. Some step size in the direction of our gradient. So that's gradient descent. And so what we're going to do is plug this into value function approximation. So for this slide, let's imagine that someone tells us v pi. Let's imagine we're doing supervised learning for a minute. Let's imagine there's an oracle that says, here's the correct value for v pi. So what would it look like? What would our algorithm look like? So if we had this v pi oracle, then we could just minimize the mean squared error. It's like the oracle says, aha, you should have done this. Your value for this state should have been 7.3, but you actually got a value of 7, so that gives you an error term of 0.3. And in expectation, over all the states that you visit, there's some expected error, and what we want to do is to adjust our parameters in the direction that minimizes that expected error, the mean squared error. So we can do that using gradient descent. So we just, again, move a little bit in the downhill direction, adjust our parameters downhill. And now our j that we're going to plug in is this mean squared error. So our objective is to minimize the mean squared error between what we thought the value was going to be and what the oracle tells us the value should be. So we want to minimize that error by gradient descent. So all we're going to do is plug that in. So we've got this mean squared error here. So how do we minimize this thing? Well, we're going to apply the chain rule to this. So we've got this squared error here. So if we apply the chain rule to this, we end up with this error term multiplied by the gradient of this error term. But our oracle is just some constant. It doesn't depend on our parameters. So the gradient of this thing is just the gradient of our function approximator, b. So we get this term here. So to do gradient descent, all we need to do is move a little bit. So forget the expectation for a minute. That's just going to be averaging over all the samples we see. We're going to move a little bit in the direction of the error that we see in each state, multiplied by the gradient. And then the way to deal with the expectation is by using stochastic gradient descent. So instead of doing a full gradient, instead of explicitly computing this expectation, all we're going to do is we're going to sample a state. So we're going to randomly sample a state by just seeing which state we visited. We're going to look at what the oracle says in that state, v pi. We're going to look at our estimate. This is what we thought the value was going to be. We're going to look at the error term here. And we say, OK, we'd like to adjust our parameters so as to correct for that error term. So we've got a step size multiplied by the error, and now multiplied by the gradient. So the gradient essentially tells you how to adjust the parameters so as to move you in a particular direction. So you've got this error that you want to correct, and the gradient tells you how to correct it. And so in expectation, you can see that if you visit all states according to a distribution under your policy pi, then in expectation, we're going to arrive back at minimizing the mean squared error. And the beautiful thing about stochastic gradient descent is that even if you change things online, then you still arrive at minimizing this particular term if you control for step sizes and so forth appropriately. So literally every single step, incrementally online, all you do is you take a step, you look at where you have arrived, you make a prediction of what your value is going to be, the oracle tells you what the value should have been, you immediately adjust your weights, and you move on to the next step. And if you keep doing that repeatedly, then stochastic approximation theory tells us that this really will move you downhill and minimize the mean squared error between your function approximator and the oracle. You're fitting the oracle's predictions across your whole state space that you're visiting. And we don't need to know or worry about this expectation anymore. Okay, so is that clear so far, apart from the fact that we've cheated? So clearly this is cheating, right? We've used this oracle. So we're going to start to deal with that. Before we do that, let's try and get concrete about what this looks like in at least a couple of special cases. So this is probably the commonest case that you see. You know, if you sample a random paper from the reinforcement learning literature, you would see an awful lot of linear function approximation using features. So what do we mean by features? Well, let's define a feature vector. So a feature vector is basically each of these features is something which is just something which tells you something about your state space. It can be anything you like. It could be like a landmark. You know, how far is my robot from each of these landmarks could be my feature vector. This could say I'm 3 meters from the wall over there, and I'm 2 meters from the wall over there. And that could be my representation of where I am in the state space. And the feature vector throws away a lot of information. I'm no longer considering exactly what I'm seeing, and I'm compressing all of my knowledge into this feature vector. But if these features are good, it can make the learning problem much easier. It could be, some trends in the stock market, or if we're playing a game, it could be, which configurations of pieces or pawns are present on a chessboard. These are all valid choices of feature vector. And each feature is just one thing, one number telling you some piece of information about your state. And the collection of these features is trying to summarize in some compact way what's going on in the state. Okay, so let's assume for now that someone gives us a good feature vector. So we're not going to address the discovery problem of where these features come from. If you want to do that, you can use a nonlinear function approximator like a neural network, or all kinds of more sophisticated methods that we won't go into. And now, how do we use these features? Well, the simplest way to make use of the features is to make a linear combination of those features. So we're going to estimate the value function by basically combining them together with a weighted sum. So this basically says I'm now going to estimate the value function of being here by saying, okay, so I'm going to have some weight that tells me how good I think it is to be a certain distance from this wall, and how good I think it is to be a certain distance from this wall, and I'm just going to take a weighted sum of those things. So, maybe I think I get one more unit of reward for each time I step away from this wall, and minus half a unit of reward each time I step away from this wall. And I would sum those together so that for any position I can work out exactly my estimate of how much future reward I'm going to get based just on those two features. And so, clearly this is not going to be a perfect representation unless our features are extremely sophisticated, but it can give a very compact and easy to work with representation of the state space. Give us a very nice way to represent our value function. So basically what this looks like then is we say for each of our features, we're going to take a particular weight. This is the jth element of our feature vector. And we're going to take the jth element of our weight vector now, and we're just going to kind of sum these things together. Or equivalently, we take a dot product of our feature vector with our weight vector, and that estimates how much future reward we're going to get. So the nice thing, one of the nice things about this sort of linear value function approximation is that the objective function, this mean squared error that we were looking at, that we want to optimize, like our measure of fit between the true value function and our estimated value, is now going to be convex. It's going to be a quadratic. You can see it's a quadratic because if we consider our parameters w, we've got this squared error here. And so if we consider our mean squared error, if we just ignore all the other terms, you can see that this thing is quadratic in w. Okay? So that means there's some bowl or other quadratic shape, turns out to be a bowl, representing basically our mean squared error, the objective function. And that's a very easy shape to optimize using standard optimization methods. In particular, if we follow gradient descent and we just move down this mean squared error, if we always take a downhill step, we will get to the bottom of our bowl. We will find the optimum mean squared error. So the nice thing about using linear combinations of features is that when we optimize them, you never get stuck in some local optimum. You always get the best correct answer if you follow your gradient descent for long enough. And the update rule is particularly simple. So we find the global optimum using this very simple update rule. And the reason it's so simple is because the gradient of this thing here is just the feature vector. The gradient of this with respect to our weights is just the features. We're just everything is linear in our weights, so we just need to multiply by our features. And so the update rule becomes very simple, which is to say the change to w, the change to our weights of our linear combination. Again, if we're given an oracle here, we're going to look at what the oracle said the value of this state would be. So I'm over here, I look at my features, I see how much I estimate. I'm going to come up with some estimate and say, okay, I think I'm going to get 6 units of reward. I'm going to see my error with what the oracle said. And now I'm going to move a little bit, step size, in the direction of how to correct this error. And what we're going to do is we're going to basically look at each of the features and say, whichever one of these features is on or highest is going to take the most credit for that error which I see. So we basically move things in the direction to adjust things by basically changing the weights which have the most active features. So if a feature is off, like imagine you're playing chess and you've got a feature to say, have I got a queen? And now you see some error in a position where you don't have a queen, and you actually end up thinking now you're going to lose the game before you thought you were going to win the game. You wouldn't update that feature because you were in a position where you didn't even have a queen at all. So you only adjust things where the features are essentially on and active. You don't make any change to situations where your features are off or inactive. Okay, so linear combination of features, very simple, very straightforward. And it basically boils down to this very simple update. You move your weights a little bit in the direction of the error multiplied by your feature vector. And the feature vector tells you how to adjust things so as to correct in the direction of where things were really on. Like if I'm really far away from this wall and I'm estimating that the further away I am from this wall, the more reward I'm going to get, then that wall, that feature from that wall is going to be, giant. That's going to be the thing which should dominate this term here. So I really adjust that weight more. Okay. Clear? I want to connect what we've just talked about with the previous classes. So I really don't want you to have the feeling that, oh, now we're talking about value function approximation, and in the last class we were talking about table lookup, and these are two totally different classes of algorithm. They're the same. Right? Table lookup is a special case of linear function approximation, and we can see that by basically defining some special features. And we can basically build up this special feature vector that says, am I in state 1? If I'm in state 1, have a feature value of 1. If I'm not in state 1, have a feature value of 0. We can do the same thing for state 2, same thing all the way down to the final state. So now we're going to have this enormous feature vector with one feature for each state we're in, and all of them are going to be 0, except for the state which we're in right now. Which is going to say, aha, I'm actually in state S734, and that one would have a 1, and everything else would have a 0. If we use that representation, if we use this X table as our feature vector, then when we take our dot product between our feature vector and our weights, we see that we're just picking out one of those weights. So we've basically got a weight for every single entry of our table. We've got a weight for every single state in our state space. And depending on which state we're in, we're just picking out one entry from our table. So this thing just lets us select the right entry from our table. And now we're back to having a table lookup representation. This is our table. Okay, we've got one entry for each state. We pick out the entry of that state according to the feature, the state we're actually in at any given time step. Okay, takeaway from this slide, table lookup representations are a special case of value function approximation. We don't need special machinery to deal with them. Everything we've seen so far is a special case of what we'll talk about today. It's just a particularly convenient mechanism to use or to think about. Okay, so we've cheated. We've really cheated. We've imagined the existence of this oracle. That's totally out of the spirit of RL. I mean, this just doesn't happen in practice. The whole point of reinforcement learning is there's no supervisor to tell us, hey, the right answer was 7.3. We need to figure that out directly from experience. So how do we do that? What's the